Good afternoon, students. Can you see my screen? Hello? Okay, 中原兵. I will give you answers after this class. You can sort out your questions and send an email to me. Professor Yang has presented the Chapter 9, Fluid Flow in Pipelines. So this lesson for the day is the tutorial for Chapter 9. First of all, I will explain 2 exercises. Then I will review what you have learned in terms of the questions asked by some students last week. Okay, now look at the first exercise. As shown in this figure, water temperature is 20 degrees, and the density of water is this value, and the kinematic viscosity of water is -6 power of 10 square meter per second. The roughness of the pipe is 0.39 millimeters and the inner diameter is 50 millimeters. The head difference in the U-type, this one, in the U-type pacematter is 0.15 meter of mercury, and the density of mercury is this value. Each elbow has a resistance coefficient of 0.6. The resistance coefficient at the entrance is 0.5, and the flow rate is 0.2 cubic meter per minute. There are 3 questions. First, determine the resistance coefficient of the wall. Here is the wall. And secondly, determine the friction factor of the pipeline flow and the total head loss. And lastly, determine the pump head and power required for producing the water flow. So now you have 5 minutes to think about how to solve these questions. Then I'll show you the solution. Try to list the steps, and you don't need to calculate the results. 1 more minute. Sorry?
For this tutorial, how many questions do we have? 3?
2 questions.
For this.
This exercise has 3 questions. This tutorial has 2 exercises. Okay, for question A, determine the resistance coefficient of the wall. We have known that wall resistance coefficient refers to the fluid through the wall fluid resistance loss, which is indicated by the pressure drop before and after the wall. Wall resistance coefficient depends on the size of the wall, the structure and the shape of the cavity. More depends on the disc seat structure. So the pressure loss in the wall is approximately equal to the sum of the pressure loss of the wall components. Right? For this question, to find the resistance coefficient of the wall between points B and C, write the pressure balance equation of the fluid in U-type piezometer according to the fluid statics, and this equation can be determined, can be obtained, right? Pressure at point B is equal to this form, and also the pressure at point C is this one. Then the pressure difference between point B and point C can be calculated as this equation, right? Change the above equation into this form. Then, according to the definition of resistance coefficient of the wall, we have this equation. According to the results we have obtained here, it can be rewritten in this form. Then write the correlation between velocity and flow rate. Flow rate is equal to the product of the area and velocity, and the area is equal to this, right? So the correlation between velocity and flow rate can be expressed by this equation. Right? Substituting it into this equation, and then we can get this equation, right? After that, change the equation into this form. All variables in this equation are known. This is the diameter of the pipe and the density of water and the mercury and the pressure drop. This is the gravity. And this is the flow rate, right? So the resistance coefficient of the valve can be determined, which is equal to 12.89. Here, please note that the resistance coefficient is a dimensionless variable, no unit. Please note that any questions? Okay. Now question B. Determine the friction factor of the pipeline flow and the total head loss. For this question, to determine the friction factor, we need to, firstly, we need to know the flow state of the fluid, right? If the fluid is laminar, the friction factor can be calculated by this equation. Right? The ratio of 64 and Reynolds number. And if the fluid is turbulent, the friction factor can be found from the Modi diagram, right? So firstly, we need to calculate the Reynolds number. The Reynolds number can be calculated by this equation. The diameter, velocity, and the diametric viscosity. The value is greater than 2,300. So the flow is turbulent flow, right? So the friction factor needs to be found from the Modi diagram, right? To find the friction factor, we also need to know the relative roughness, right? It can be calculated by this equation. The roughness of the pipe has been given. The roughness here. And and the inner diagram, the diameter, has also given. So the relative roughness can be determined. And then from the MODI diagram, find the relative roughness from here and the Reynolds number from here. Then you can find the friction factor, which is equal to this value. So after finding the friction factor, the total head loss of the flow can be determined. The total head loss in this question include the major loss and minor loss, as well as the head loss occurs in the valve between point B and C. Right? Here also had head loss.
So this is the general formula, right? For the total head loss.
This equation. Right.
General.
Major and minor. And head loss occurs in the valve. Which is equal to 3.96 meter. The method to calculate the major head loss, minor head loss have been presented by Professor Yang, right? In chapter 6. So if you don't know how to calculate it, please review the basics of chapter 6. And now, question C, determine the pump head and power required for producing the water flow. How to solve this question? Firstly, write the energy equation between the water tank surface and the outlet of the pipe. Right? This one. From the figure, we knew that pressure at the water tank surface and outlet of the pipe are equal to 0. Here and here. And velocity at the water tank surface is also equal to 0. Right? Then velocity at the outlet of the pipe can be calculated through the flow rate and area of the pipe. According to this equation, right? The continuity equation. Then the velocity at the outlet of the pipe can be determined. Due to the flow is turbulent, we have find in question B, right? So the kinetic energy coefficients are equal to 1. Alpha 1 and alpha 2 equal to 1, right? So with this information, this equation can be rewritten in this form. Right? Then substitute the equation for the correlation of velocity and flow rate. It can be changed into this form. Right? Okay, let's go on. From question B, we have known that the total head loss is 3.96 meter, right? And we also knew that flow rate is flow rate is 0.2 cubic meter per minute, and the height of each part is also shown in this figure. This one, here, right? So substitute the known information into this equation. The pump head can be determined, right? Which is equal to 5.6 meter. So the power gained by fluid can be calculated by this equation. I think you have learned this equation in chapter 8. Any questions? No? Okay. Now, exercise 2. A centrifugal pump is to be placed above a large open water tank, as shown in this figure. This is the water tank, and is to pump water at a rate of 0.015 cubic meter per second. At this flow rate, the required net positive suction head is 5 meters, as specified by the pump manufacturer. If the water temperature is 20 degrees and atmospheric pressure is 101 kilopascal, determine the maximum heat. Determine this heat, the maximum heat, this part. That the pump can be located above the water surface without cavitation. Assume that the major loss between the tank and the pump inlet is due to filter at the pipe inlet having a minor loss coefficient 20. Other losses can be neglected. The pipe on the suction side of the pump has a diameter of 0.1 meter. Try to solve this question. How to find the maximum heat? This part. List the steps according to the given information. I'll explain this exercise 3 minutes later. Please note that for this question, the major loss is equal to the minor loss, and other loss can be neglected. So the total head loss is the minor loss. Okay, for this question, we have known that the flow rate of the pump is 0.015 cubic meter per second, and the required net positive suction head is 5 meter. Also, the diameter of the suction of the suction side of the pump is 0.1 meter. What's net positive suction head? We have known that the net positive suction head is the difference between the total head on the suction side near the pump impeller inlet and the liquid vapor pressure head, right? Available net positive suction head represents the head that actually occurs for the particular flow system. In addition, we have known that cavitation occurs when the liquid pressure at a given location is reduced to the vapor pressure of the liquid. So, to avoid cavitation, the required net positive suction head must be maintained or exceeded. So, the maximum value for the heat, this part, will occur when available net positive suction head is equal to the required net positive suction head. To avoid cavitation, the required net positive suction head must be, need to equal to the required net positive suction head for this question. I know. The contents is here. This is the equation to calculate the available net positive suction head. Which you have learned. Sorry, wait a moment. There are some problems in the slides. Okay. The maximum value for this part will occur when available net positive suction head is equal to the required net positive suction head, right? Because of this. You have learned in chapter 8. So the water temperature is 20 degrees. From the saturated water steam table, the vapor pressure of water is 2,337 par, and the density of water vapor is 0.017 kilogram per cubic meter. This variable is the head loss. For this question, we have known that the major loss between the tank and the pump inlet is due to filter here. It's due to filter at the pipe inlet. So the major loss is equal to the minor loss, which is the only head loss to be considered just for this question. The velocity of the water in the pipe can be calculated through the ratio of flow rate and area, right? Which is equal to 1.91 meter per second. We have known that the minor loss coefficient is equal to (20), so that the head loss can be calculated. So, from the above information, the maximum value for the heat, this part, can be determined, and the value of it is equal to 1.34 meter. So to prevent cavitation with its accompanying poor pump performance, the pump should not be located higher than 1.34 meter above the water surface. Okay, any questions for this question, for this exercise? No. Now I'd like to review what you have learned in terms of the questions asked by some students last week. First, the Bernoulli's equation. Bernoulli's equation can be derived from the principle of conservation of energy with additional assumption that the density remains constant, which means a very good assumption for liquids and also for gases if the speed is not too high. The speed is not too high. Bernoulli's equation assumes the following simple representation for steady inviscid incompressible flow, which is an ideal flow. So the Bernoulli's equation can be written in this form, right? Where these two variables are the pressure head, and these two variables are velocity head, and the z is potential head or elevation head. Please note that this equation is the piezometric head or hydraulic head. Please note this. After that, the total head is the sum of the pressure head, potential head, and velocity head. It can be calculated by this equation. It also means the Bernoulli's equation express the energy for a steady inviscid incompressible flow is constant. Bernoulli's equation also can be rewritten in this form. Right? The previous form times density and gravity. It can be changed into this form. Here, P1 and P2 are static pressure, and these variables are dynamic pressure. And these two equations express the piezometric pressure. These are piezometric pressure. So rewrite the equation in terms of piezometric pressure. The Bernoulli's equation can be changed into this form. Right? Based on Bernoulli's equation, the flow rate can be measured by a volumeter. In addition, one of the exercises in tutorial 7 needs to be revised. This tutorial. The elevation difference between the approach section and the throat section was ignored, but in fact, for this question, the two heights are not neglected. Please note take point 1, the approach section, as the reference point. So height at point 1 is 0. So that his metric head at point 1 is 1 meter. Height at point 2 is not 0, but the piezometric head at point 2 is equal to 0.5 meter. This means on each side of the energy equation, the potential energy head is combined with the pressure energy head. Here, remember. And also, this need to be remembered. So the tutorial exercise 7.1 can be solved step by step. Any questions? Okay, that's all the contents of this tutorial. Thank you.